This is probability. And it's just simple, what's the chance of pulling a rabbit out of a hat if you've got two rabbits in the hat? And it isn't actually used much for what we need to do. And it's kind of boring because all it is a bunch of definitions. Probability is the chance of a particular event happening. And this can be, a classic probability is like flipping a coin, heads or tails, right? Because everybody knows that one. A non-classical or an empirical probability is the probability that it's going to rain. We don't know that. We can estimate it. They do it all the time on the news. It's just a matter of whether you know what's going to happen or not. And for most things, like coins or dice, that's not interesting because we know all about it. The chance that it's going to rain, or the chance that your airplane will crash, or something like that, that's actually much more interesting, at the very least. And one thing about this is that what we see is not always what there is. And this is the odds ratio, and this is common to horse bets. So that if you've got a chance of 2-1, then that means that in 3 races, this horse wins twice, or 50-1. In 50 races, this horse wins once. All right, so those are long odds. An odds ratio is just add those two together and divide that into the first number. So 2-1 is 2 out of 3 chances of winning the race. A sample space is the way anything can happen for what my experiment is. And this is like flipping coins. We got 2 coins. You can get a heads or you can get a tails. So the sample space, the range of possible events, is heads and heads, heads and tails, tails and heads, tails and tails. And the reason for this is just so we can say what is the chance of getting 1 tail and 1 head? Any order. So that's 1/2. If we could list the sample space for everything, we could estimate the probabilities better. But like the chance of rain, how much rain? Is it yes or no? Is it a lot or a little? What constitutes rain? How much do you have to get? If you walk outside and it's sprinkling, is it raining? The sample space is just what can happen, and it helps figure out what the odds are on something happening. This is the sum of 2 dice. You ever play craps? You roll 2 dice. The shooter, the one with the dice, rolls the dice and gets a point. Whatever they get the first time is their point. Then they roll again until they get their point again. Or a 7 or an 11 comes up. 7 or 11, you lose. Shooter loses. So if I roll a 2, I have to roll a 2 again before I get a 7 or an 11. So what's the chance of getting a 2 again versus getting a 7 or an 11? Here, there's 36 possible ways this can happen. So the chance of a 2 is 1 out of 36. The chance of a 7 or an 11 is 636 plus 236, or 836. So the chance of a 2 is really small compared to the chance of getting a 7 or an 11. Also, if you roll a 7 or an 11 on the first roll, you lose. So you've got to get something other than 7 or an 11. Your best chance is to get a 5 or an 8. the first time. Then you've got at least a 5 30-second chance versus a 8 30-second chance of getting your point again. This is just the way things can happen, and if we can list it, we've got a shot at controlling or estimating it. Then there's things like this. This is the complement of an event. Is 1 minus the probability that the event occurs. And the only reason for this one is that sometimes it's easier to find the complement rather than find the number that you want. This is the basic rules. Or means add. What's the chance of getting a heads on a coin or getting a 4 out of a deck of cards? What's the chance of getting a head? 50-50, 1/2. What's the chance of getting a 4 out of a deck of cards? How many 4s in the deck? 4. 4 4s. That works out. How many cards total? 52. So the chance of getting a heads or the chance of getting a heads or a 4 is 4 50-seconds plus 1/2. Or means add. So anytime there's an or, you add. The chance of heads and the chance of getting a heads and a 4. And means multiply. So that the chance of getting a heads and a 4 is 1/2 times 4 50-seconds. And means multiply or means add. That's pretty much the basics of that. One thing that comes into this dependent or independent probabilities. The chance of rain and the chance of getting a heads on a coin is independent. They have nothing to do with each other. If I have a deck of cards and I draw a 4 the first time, I take my 4 and I put it down and I draw another card out of the deck. What's the chance of getting a 4 again? Chance of the first one is 4 out of 52. What's the chance of the second one? 3 out of 51. So that is not independent. It is a dependent event. The chance that this happens affects the chance that this happens. And they always do this. I've got 5 red M&Ms, 6 green, and 3 blue. What's the chance that if I pick one at random that it's red? How many things can I pick up? 14. That plus that plus that. So the chance of getting a red one is 5/14. If I put it back, the chance of getting a red one is still 5/14. If I don't put it back, then it becomes a dependent event, and I get 4 out of 13. The easiest way to do probability is to look at a contingency table. A contingency table has all the possibilities of one here and all the possibilities of the other there. And you can do this for heads and tails or rain or not rain, any kind of thing here. So there's a probability. I can start with numbers and get a probability for each one of these things. So that this, what is the chance that someone owns a dog? Look at the dog row. There's a 45% chance that someone owns a dog out of this sample. The chance that someone owns a cat is 52. The chance that someone doesn't have a cat, the complement is 1 minus the 52 is the 0.48. Make a contingency table. Now this one, people can have dogs and cats. So what's the probability that they have a dog or a cat? Or means add. So what's the probability of having a dog or having a cat? Look at the dog. What's the probability of dog? What's the probability of cat? 0.52. Then I've got 0.52 plus 0.45. But I've also got people that have both. So I have to subtract this probability because these are not independent events. The probability that it's going to rain or I get ahead, I can add those. But this, and the contingency table covers all these silly formulas. The probability of a dog or a cat is that plus that minus that, because that's the overlap. And when they do the Venn diagrams, they show an overlap. That's what we got to remove. This is multiplication. And means multiply. And we're back to contingency tables. If you can get it into a contingency table, you got it made. Right? We've got a 2 by 2 or a 2 by 3. When you get on Google, Chrome, what comes up? Before you do anything, you just click on it and say, start. What comes up? Look what came up here. I just went to Chrome. It knows I used MyOpenMath. And it's got a couple other things because it doesn't have a history. When you buy something, you go to Amazon and you click on book, some kind of book. It says, people who bought this also bought. You've seen that. There is a huge contingency table for you. For everything you ever bought, everything you ever looked at, how long you looked at it, whether you bought it or not. Did you buy it on the first shot, the second shot, or the third shot? So that there's 1,000 rows and columns on this thing, multidimensional, that you fall into. So they're looking at the probability that if you did this, then you might like to do all these other things. All the recommender systems are huge probability models, contingency tables. So that this kind of thing is an excellent way to look at probabilities. And this is the way that, to me, this is the easiest thing to do because you can figure things out. Right, we've got ice cream preference for children and adults. All right, I made these up. I have no idea what ice cream preference is. Who likes vanilla? Who likes chocolate? What's the chance that a child likes chocolate? What's the probability that a child chooses chocolate out of this sample? How many are children and like chocolate? Every one of those boxes is that and that. So this is adults who like chocolate, adults and chocolate, adults and vanilla. What's the chance that if I draw an individual out of this, that it's a child that likes chocolate? This is how many people I got. So the child liking chocolate, there's 57 out of 191 individuals. What's the chance that it's a child? Chocolate or vanilla? That's the 85 over 191. I can convert these all to probabilities by dividing each one of them by the total. This is the way that the recommender system clicks into when you click on something. It says, whoa, look what you did. You like chocolate. You're over 8 or 12 or whatever. Therefore, and then it goes back in another dimension. These are the individual things. These are the probabilities. Every one of them is divided by that 191. Here's the useful thing. This is conditional probability. What's the chance of a child given that you've got someone who likes chocolate? This is the condition, likes chocolate. What's the chance of a child given that they like chocolate?
30%.
Here's a child. How many are in chocolate? The given condition restricts the row or the column. And when you get into Google and look around for things, it says, you're here. You got here this way. That's a given. You're already in a category. So the probability that got a child, given that they like chocolate, becomes this divided by the proportion that like chocolate. This is a conditional probability. The condition restricts the row or the column. Here's the probability that a individual selected likes chocolate given that it is a child. I have a child. What's the probability that they like chocolate? Now I've got the other direction. There's my 0.3. But now, given that it's a child, it's over here. The conditional probabilities are the most useful ones because these are the ones that actually are used. Insurance company. You go to buy insurance. They ask you, have you had any accidents? My brother-in-law never saw a car he couldn't wreck. He goes to buy insurance. They say, how many accidents have you had? Then they look at, given that he's had this many accidents, what are they going to charge? So the condition is very common. What's the probability that something occurs given that another event occurs? And this is the most deepest kind of dependence. Because if children and chocolate, adults and vanilla have nothing to do with each other, This table is just split in 4 ways, so that the probability of a child and chocolate would be a product. Here, the probability of a child, given that they are in the chocolate column, is 0.3 over 0.52. So the given condition restricts the probabilities to a row or a column. Or in a multi-dimensional, I mean, these things got like 500 dimensions. Everything you ever looked at, everything you ever bought is in there somewhere. And this is something that Google makes a lot of money on. They sell this information. You go to Kroger or Food Lion, you got a little card, you scan, they give you a price break, right? They are your friends, right? They know what you bought. And there's a coupon dispenser right next to it, right? You get your receipt and you get a coupon. What kind of coupon did you get?
Something I like.
Something you like. Something that is related to something that you have bought before. If you always buy bananas, regardless, every time you go to Kroger or Food Lion, you buy bananas, it's going to give you a banana coupon or some kind of fruit or some kind of fruit cup, so that the conditional probability is the way the world works. Given that you have crossed the street out to your car, how many times? 100 this semester, maybe. What's the chance that you're going to get hit? Given that you haven't been hit yet, that chance is pretty low. If you are constantly being run into by cars, it's not looking good. Conditional probability is the way that everything actually operates. And we've still got the and the ors, but we take them in different things. What's the probability that we've selected someone at random that likes chocolate and we've flipped a head on a coin? Here's the conditional probability. I've got chocolate given, it's a child, and the coin flip is 1/2, and it's and. It's 0.57 times 1/2. And means multiply, or means add. And it doesn't matter what those probabilities are or where they came from. Stoplights are set up like this. You're going up to a stoplight, it's red, and you get in the left-hand turn lane, you're the first car there. You're going to get a green turn light. What if you pull up after the light has turned for the main lanes? You're not going to get a turn light. This is a conditional probability. There was no car there when the light was deciding what to do. The condition is that there is a car or not in the left turn lane when the light is deciding what to do. So a conditional probability is much more important than any other probability. Condition restricts you to a group. Given that you've had one accident, you are in the one accident group, then what else occurs? Do you need a new car? Are your insurance claims small? Your insurance claims big? Given that you've had 2 accidents, we have a new condition and you go into a new category. A conditional probability restricts your place in these probabilities. Show you this. This is confusing. This is the way the logicians and the statisticians do these things. They don't use children, adults, and ice cream. they use A and B. And this is the typical setup. A and not A. This is a not A in logic. B or not B. Probability of B and A is here, just like the probability of a child and chocolate. So the A and the B are generic versions of something real. A and not A, B and not B. We add here, the probability of A is A and B and A and not B. Probability of not A is over here. This is the probability of adults in this table. Probability of adults is 0.22 plus 0.33. So this is what's going to show in the homework. One of their favorite problems looks like this. This is a conditional probability. The probability of B given A occurred. All right, the way to do these things, this is 0.72 probability of A, 0.72, and this is the notation, P with the event, probability of A, probability of B, 0.18, probability of A and B is equal to 0.1. This is the way these things work. This is kind of the setup for a probability distribution. This is the probability of A and B. Probability of A and not B. Probability, this is A, not A, B, not B, not A and B, probability of not A and not B. This is probability of B, probability of not B, probability of A. I add across all the events that A is involved in. I get the probability of A itself, probability of not A, and this is 1. All right, so in this thing, they give you the probability of A. That's 0.72. That's the total across A. The probability of B is 0.18. That's the total across or down B. The probability of A and B is 0.1. That's 0.1. All this is a way to confuse you by making the table weird. What's the probability of B? I think that's the problem. B given A. What was it? Here it is. Probability of B given A. So the probability of B given A is conditioned on A. So the probability of A is 0.72. What's the probability of B given that you're in the A column? The probability of B, given that A has occurred, the probability of that B given that you're in the A row. So they just give you 3 parts of the table, which actually you can use to calculate all the rest of the table. Here's point 1 with a total of 0.72. What's got to be in the, this is B, what's got to be in the not B column or cell? It has to add across. So this is B and not B, and we're in A. Probability of not A and the probability of B is 0.18. What's the probability of not A and B? Here's the total. That plus that have to equal to 0.18. So that's 0.08. This all has to add to 1. So what's the probability of not B? This is the probability of B. The probability of not B is that plus that has to equal to 1. So this is 0.82. 0.72 plus this has to add to 1. I think that's 2.8. And the probability of not B and not A, I can get going 2 directions. Hopefully it adds up. That's probability. That's as exciting as it gets.